Okay. Right. Okay. Okay. Sorry. Yeah.
Okay. Yeah. Each node is composed of a linear function and activation function, which then determines which nodes in the following layer get activated. Okay, there are various types of neural networks like ANNs, CNNs, and RNNs. These are some of the applications that we have for the neural network. Okay. And
Alright, so what are the core of traditional machine learning models is that typically when humans read, when we look at our assignments, read paragraph to paragraph, we understand the next word, the next sentence. We basically get the context based on what we understand from the previous words that we've read so far. And our thoughts essentially have persistence. But for traditional machine learning models, this persistence is lacking essentially. And the traditional neural network model is unable to use contextual knowledge about its previous events to help it down the road. And yeah, that's one of the shortfalls that machine learning models has. Yeah, so what are recurrent neural networks? Well, basically a machine learning network with loops in them. As a result, this allows the information to persist, similar to human thoughts. And this is basically how a chunk of a neural RNN looks like. It has takes in input XT and outputs a value HT. And what's different about it from typical neural network is that it has a loop around A, which is where the model is. So let's unroll the loop. When you unroll it, you see the loop actually allows information to be passed from one step of the network to the next all the way to the end. Yeah, and sometimes, especially for language models, we need to look at recent information to perform the present task. So for example, let's just say our model can predict the next word. We say clouds are in the. And it's pretty obvious that the word is sky because there's the word cloud here to give away the context of it. In this case, the gap between the relevant information and the place where it's needed, like sky, is very small. It's only like a matter of like 4 to 5 words. So RNNs actually specialize in learning to use this past information. But why don't you just use RNNs? Why do we need to bother learning about LSTM or whatever this is? Yeah, there are cases where we need more context over longer distances. So like consider this flowing text. It says I grew up in France. Then after this you have a whole paragraph of text, followed by I speak fluent. Now obviously we look at the word speak to infer that what we're looking for is a language. And then obviously the context needed is I grew up in France, which is at the start of the paragraph. And then as you can see, it's a very long distance away. It's an entire paragraph worth away. And this is what happens and this is where the gap between where the information is needed and where the information is becomes very large. There's a very whole big chunk of text in between. And by right, in theory, an RNN is capable of handling it, but in reality, as tested by several machine learning specialists, recurrent neural networks are unable to do so. So now I'll go on to an LSTM to actually perhaps improve on this issue. But what are LSTMs? LSTMs basically long short-term memory networks. Usually I call it LSTM short form. A special kind of RNN explicitly designed to learn long-term dependencies. And remembering information for long periods of time is what LSTM specializes in, as the name suggests. So RNNs take the form of a chain of repeating modules of neural networks. And in standard RNNs, it's a very simple structure. It just contains a single hyperbolic tangent layer. But however, standard LSTMs actually possess 4 interacting layers, which you can see there. And the 4 layers consist of the get gate, the input gate, the cell state, as well as the output gate. So let me just go through how the diagrams actually work. Each line actually carries a vector from output of one node to another. And the pink circles represent pointwise operations. These pink circles here, like vector addition or multiplication. The yellow boxes are neural network layers. And the merging lines simply indicate concatenation, and the morphing lines denote content being copied and the copy is being sent elsewhere. So this is the core mechanism behind LSTM. This cell state, this is my horizontal line going through the entire chain, and there are only minor interactions to this cell state, and makes it very easy for the model to actually pass information along time change. And in this case, CT-1 and CT is actually basically referring to the cell state for the previous and the current timestamp respectively. And what the LSTM actually has is that it possesses the ability to add and remove information to the cell state which is regulated by structures that we call gates. So what are gates? Gates are essentially a way to optionally let information through and are composed of a sigmoid neural network layer and a pointwise multiplication operation. And an LSTM actually has 3 of these gates to protect and control the cell state. What's a sigmoid layer? A sigmoid layer basically outputs a value between 0 and 1 and designates how much information to let through. So let's just say it has 0, meaning it's not going to let any of the information through, and 1 means it lets through everything. Yeah, so the first gate is basically the forget gate layer. And the first step is to determine what irrelevant information do you need to forget or throw away from cell state. And this decision is made by the sigmoid layer here, called the forget gate layer. And it looks at the previous hidden state, the input, and outputs a number between 0 and 1 for each number in the cell state. Yeah, so this is the equation. Basically, what happens is that after taking the input, applying the bits to it, when you add in the bias, then the sigmoid layer there to basically come like act as a filter to determine how much information to let through. This is an equation that we use very commonly later on, and then I'll point it out to you later. Notice how similar this equation is to the others. Yeah. So now the second step is to decide what new information to store in the cell state. Previously we talked about throwing away information. Now let's talk about taking information. So firstly, there's a sigmoid layer called the input gate layer that determines the importance of the new information input. And there's another hyperbolic tangent layer that creates a vector of new candidate values that could be added to the cell state. Yeah. Third, remember about the equation I talked about just now. You can see here this equation is the very same equation that in the forget gate layer. It's basically acting as a filter again. And then this equation basically is an equation to create new candidate values. Yeah. And the third step is to update the cell state, this horizontal line going through. So we multiply the old state by ft, which is a forget gate layer. That forgets the things we decided to forget. All the useless, all the irrelevant information, just throw away. And then we add in it times the current cell state, which are new values. So we take in all the new information, and then we just scale it by how important each value to be, and then add it to the cell state. Wow. So we take in new stuff, and at the end of the day, we also forget new stuff. Yeah, this is the general equation for it. And then the final step to decide what values to give as output. So we run it through a sigmoid layer again. Previously, we used a lot of sigmoid layers already to decide which part of the cell state to output. And then we run the cell state through a hyperbolic tangent layer, and then multiply it by the outputs of the sigmoid gate. So you can output only the parts that you want. As usual, we see this equation again, it's the same from the forget gate layer and the second layer. And then afterwards, yeah. So what can LSTM be used for? Well, they can be applied for a variety of users like speech recognition, language modeling, and even stock price prediction, which NUS FinTech loves doing. And then it's a very effective model, and it's one of the fundamental tools in machine learning. Well, what are the shortfalls of LSTM? Well, basically, it requires a lot of training time and computational power. And LSTMs actually do not completely remove the validation gradient. They only just reduce the issue. And sometimes the model, just like normal human beings, they might actually forget the wrong information through the forget gates. Furthermore, the LSTM are also particularly prone to overfitting. And let's just say to counter overfitting, try putting a dropout algorithm, it's also difficult to implement. Yeah. So is there a more easier model to train and run? Is there something that's less computationally taxing? Of course, there's something called GRUs, which my team leader will go through now.
Yeah. So basically I'll be sharing with you guys what a GRU is. So a GRU is also known as a gated recurrent unit, right? So it's a gating mechanism in recurrent neural networks. And it acts very similarly to an LSTM, as Anthony has mentioned, just that it has much less parameters due to lack of the output gate, which I will mention later. And as a result, right, it's less computationally taxing, which is one of the shortfalls of LSTMs, as Anthony has pointed out. So GRUs are also specialized in tasks like natural language processing and speech signal modeling. Yeah, so this is a comparison between LSTM and GRU. So as you can see on the left here, we have the LSTM, which has 3 main gates. So the forget gate, input gate, and output gate, which Anthony has shared earlier on the functionalities of. Whereas you look on the right, we have the GRU there. So it looks fairly similar, just that it mainly has 2 gates, the reset gate and the update gate, which basically functions similarly as compared to the forget gate, input gate, and output gate in total. But you can also observe that there is no cell state. So what it does is that it only passes the hidden state. There's only one state moving from one node to the other. Yeah. So the reset gate, right? I mean, sorry, the update gate, right, focuses on it's like it focuses mainly on the long-term memory, basically deciding how much information is to be remembered and passed on to the next node. Whereas the reset gate, as the name suggests, it decides how much information and what information is to be forgotten. Yeah. And it really captures the short-term memory, which is like the short-term memory side of things. Yeah, so in this diagram, you can see that the first step, right, basically is to generate the output of the reset gate and the update gate. So the reset gate basically decides how much information can be forgotten. You can see by this equation here. So what it's basically doing is taking in the input, which is xt, and the hidden state, which is ht minus 1, and applying the sigmoid function on the weighted sum of them. Yeah. Then followed by the update gate. Sorry, previous slide. The update gate. Okay. Yeah, the update gate which decides how much, I mean, this is what information is being passed along. Okay, so it's shown an exact figure. Or it's like, yeah. So after that, we have to get the output for the candidate hidden state, right? And this candidate hidden state basically applies the hyperbolic tangent function to the output of the reset gate, as you can see here, R2, right, which is the output of the reset gate. Then you apply this hyperbolic tangent function, which basically basically decides what information is being forgotten. So in this step, right, it basically forgets all the information that needs to be forgotten from the previous steps. Yeah. Next slide. So after we are done with getting a candidate hidden state, right? So as I mentioned so far, we have only gotten the output of how much you need to remember, how much you need to forget, and you have also forgotten the information that you need to forgotten. But we haven't decided on what needs to be retained from the current state and the previous state. So this set basically what it does is that it uses it just basically does element-wise convex combination of ht and ht minus 1, which is all the current state and the previous state, and then basically decides what information and how much information is to be retained to be passed on to the next node as the ht minus 1 for the next. Yeah. So as all models do have, like we all have shortfalls, right? So as compared to LSTM, the main shortfalls of the GRU, the data retrieval unit, is that it converges very slowly and it's very prone to underfitting. Yeah. Moving on to the doing like a mini walkthrough of project that we done earlier on human activity recognition. So basically what this project, this mini modeling that we did does is that it basically predicts human activity using handphone accelerometer data. So what this means is that, you know, when you hold your handphone, right, the way when you move your mobile devices, this accelerometer in the phone actually captures like the different angles and the speed, the velocity of how the phone moves. So we are basically using only data and trying to predict what kind of activity the user of the handphone is doing at the current point in time. Right. So these are just reporting some of the libraries. And this columns array, right? This list of columns basically whatever that we're going to be using to study our to predict. So user is the user ID. So in this case, in our data set, we have 36 users. Activity is that the result. So basically what activity the user is doing at the current timestamp. And the x, y, and z axes are just the values captured by the accelerometer. So right now we're describing the data set to just basically have a summary statistic of our data set. But we realize that, we realize that you don't see the z-axis, and I'll explain further why it's not there. So before I explain further, we check for null values. So we check that there's one null value, so we just remove it. So very simple. First part, this part, we plot the data types of each column, and we realize that the z-axis is actually an object data type, which is not what we would expect, because the x and y axis, right, and z-axis, they're all taken from the accelerometer. So we expect them to be of like a float data value, but it's in the object data. So what we're doing subsequently is basically to convert the object data to the float data set. Yeah. So here, we're basically cleaning the data. So after we clean, you can see that we have successfully converted it to the float data. So now they are all aligned in terms of the data type. Yeah, so this is the new and clean data. As you can see, everything they're all in the values. The values are basically the X, Y, and Z axis together. The user, we have 36 users, activity, and time span. Yeah. So moving on, we are gonna do some exploratory data analysis, basically to understand our data a bit better and to find out whether there are any class imbalances in our data. Alright. So in this graph here, this bar plot, we're basically plotting the amount of data by activity. And this evidently shows us that we have way more data on walking, jogging as compared to upstairs, downstairs, sitting, and standing. So what upstairs and downstairs is basically walking upstairs and walking downstairs. Things standing, walking and jogging, they're just relatively self-explanatory. But from this you can see that see, like we have over 400,000 data points for walking, over 300,000 for jogging, whereas compared to like upstairs, downstairs, sitting and standing, there's way less data. So this is an evident case of class imbalance, and having this sort of class imbalance in our data will skew our data in the sense that yeah, you will affect the results and you'll make it less accurate. So I mean there are two ways to fix this for sure, right? But in this case we implemented smooth, which I will talk about it, which I will talk about a bit later at the bottom. I will continue with the exploratory data analysis first. So this one we are plotting how much each user contributes to each activity. So as you can see here, we have 36 users, and each user, this is not a very, very good plot, but you can see that the activity that each user contributes are relatively disproportionate. So it's not the same across. Yeah. Okay, so this part might seem a bit confusing. So basically what we are doing is that we are zooming in one user in this case, just to see how the X, Y, and Z axis for each activity varies across time. Right. So for walking, you can see that this is for X axis. You scroll down a bit, you can see the Y axis and the Z axis. And as we would expect, right, the frequency of the graph should be relatively constant. As when we walk, we usually walk at a relatively constant pace. So as expected, when we plotted it, you can see that it's relatively constant. You know, the frequencies are not that different across the time. So scroll down. This is for Y axis. And scroll down. And you can see this on Z axis. So now, like you guys to think, if walking is like that, how would you expect jogging to be like?
Way faster, because that's good faster.
Yeah, so it will be a higher frequency, right? So if you scroll down, as we expected, you can see that the frequency is definitely higher for X, Y, and Z axis. Yeah. So this is the data for upstairs. Scroll down. Then you can see the data from downstairs. You can see the data actually for upstairs and downstairs, they're relatively similar. So that could be an issue for us because it means that the model might predict it less accurately. Yeah, might confuse upstairs with downstairs. So as compared to walking and jogging, for sitting, we expect it to have like lower amplitude, right? Because you won't be moving as much when you're sitting down. You won't be moving a mobile device as much. You won't be swinging your arms. So as expected, this is what we have. And yeah, and we also have for descending, which is just in between, basically in between walking and yeah, so this part, basically we're implementing synthetic minority oversampling technique. So what this technique does is that it basically creates synthetic samples to generate samples for the other classes so that we can get them to a level playing ground in the sense that they will all have equal number of data points. Yeah. So as you can see after we're done with this mode, we bumped it up all to above 400,000 data points for the other activity. Yeah. Pass the time to Anthony to share.
Yeah, so now that we actually clean our data, the data set is proper and nice, neat and tidy, we can start on the data pre-processing, and we can start reshaping the data for our model. So now I'll go through some of the hyperparameters. So this is basically just a seed. Seed is basically, we set it at 42, it's just a random number. We just set it there so that we can reproduce results neatly. And then afterwards, we have these two features that I'll go through later, something called time steps and set. These two are related to the sliding window algorithm that we use, and then I'll go through it later. And then afterwards, we have three features, mainly the X, Y, and Z axis. There's six clusters we need to predict from. The walking, jogging, upstairs, downstairs, sitting, and bending. So those are the six clusters. Then we're using 50 epochs to train our model. And then these are the batch. The batch size, learning rate, and the log. All these hyperparameters down here are just parameters that we tune to obtain the best results. Yeah. So let me just give you a brief introduction to the sliding window algorithm. So basically, how it works is that let's just say you have an array like A, B, C, E, F, G, all the way to H. And then let's just say each window has three characters inside, A, B, C. So how this window will actually slide, just like the name says, is that you go from A, B, C, then it takes one step to the right, B, C, D, then one step, D, B, E. So just now, we're going through the hyperparameters. I missed out two hyperparameters, right? Yeah, so basically what time step is just indicating the size of each window, and then the step is just indicating how big of each step, how much each window is going to slide. That's basically what it means. Yeah. Alright. Okay, so yeah, this basically we just using this to actually just reshape the data and everything. And then this is for the smooth. Smooth. So in this case, we are using a sliding window because the windows are, in other words, the windows are overlapping when we slide it across. In this case, 80% of the data is actually overlapping. And this can actually help the model to make its prediction more accurately. And in this case, since the set is 10 and then each set is samples, as I said before, 80% overlap. Yeah, and then let's just say this window has like 60% of the data belonging to standing, and then the other 40% belong to sitting. Then what's the label they apply to the window? Well, basically, the label assigned to each window is the activity that occurs most frequently in this window. So let's just say 50% of it is standing. We straight away just label the window as standing. Yeah, pretty much that. Now, this is just for me, but personally, to take a look at the shape of data. Then afterwards, we split the data into training and testing sets. So similar like how one would prepare for the exam. Like you prepare for an exam, right? Obviously, you're not going to go through all the papers without timing yourself. You obviously have to go through like what, four out of 5 papers. You know, you just practice. Then the last paper, you probably want to time yourself, test yourself. Similar for models, you need to like train up that way as well. So in this case, you're doing 80%, using 80% of the data set for training, that's 20% for testing. Yeah. Then afterwards, this is where we build the model architecture. We put one LSTM layer, another dropout layer to try to prevent overfitting, and then a couple of dense layers to basically, what basically what dense layers are is that they basically contain neuron and it computes the weighted average of its input, and its weighted average is then passed through a non-linear function called an activation function, which determines whether the neuron's input is actually the network is actually important. So basically, this is all just getting all the key features, all the important things that the model needs to remember. Yeah. Before making its conclusion, or as to predict, this activity, what is it? So this is just an overview of our model. Yeah, as you can see, there's 26,000 trainable parameters. Higher trainable parameters basically just means that there's a higher chance of overfitting. Yeah, and then that's why we put in a dropout layer. We try to avoid it. Afterwards, this is where you start training. Then I train, as you can see the loss increasing, the accuracy increasing as you're training it. Yeah, and then the whole training process took around 2 hours. Yeah, very taxing for my computer. And then afterwards, I plotted a graph to check to actually see how the model progressed throughout the entire training session. So you can see the accuracy is gradually increasing and it's staying there. Then the loss is gradually decreasing. This is just to make sure that nothing wrong or nothing fishy is going on while you're training the model. And afterwards, we did an overall test, and then our model managed to reach around 94% accuracy with the loss actually below 0.2, which is pretty good in our opinion. Yeah. And afterwards, to find out the weak points of our model, we analyzed it using a confusion matrix, which is our confusion matrix inside also has a heat map. So yeah, that basically just makes it easier for us to read. So I'll just talk you through how a confusion matrix works. So basically, this is just analyze the true positives, false positives, this sort of thing. So as you can see here, right, for jogging, sitting, standing, and walking, most of the predictions made are pretty accurate. But for downstairs and upstairs, as you can see, for downstairs, right, for downstairs, which basically is here. As you can see, it made 1,439 predictions wrongly out of possible 8,000 predictions, which is a pretty high inaccuracy rate. And the same issue is with the upstairs. We also made a lot of wrong predictions and caused it downstairs. So yeah, this is just a issue that our model faces, and at the moment we believe that it's not an issue with our model, it's more of an issue with the data set. So yeah, this is just a table showing the overall accuracy for each activity. Yeah, we come to the end of our presentation. Are there any questions?
So in the works with the LSTM, how do you determine when you use the high quality scan and you use the sigma? Because the shapes are very similar, right?
Sorry, the shapes are different. No, it's in the. You should referring my site, is it? How the last game is built, is it?
Yeah,
Right.
when you use the tannage and when you use this.
See, more of that. Those are. You're referring to the model architecture or
Yeah, the
architectural changes?
I think it's the slides.
I think
It's
it's referring to architecture. Just go up.
Or architecture.
Yeah. Referring to this one?
no, I mean the slide.
It's the slides, right?
Okay.
I think I'm more.
For the LSTMs, all these layers are already inbuilt already. We're not building the LSTM from ground up. We're just using a pre-trained, not really pre-trained, more of like a template of the LSTM, just putting into our model for us to use. Yeah. This is just explaining the insights of it. So basically you can see this as a black box. And then we're just as us as a client, someone has implemented this. And then all these things are hidden in a black box, not really for us to touch and play around with. And then we are the client, we're just using it to implement our model. Yeah.
Well, actually, I have a question. Yeah, so just now you mentioned you have three parameters, hyperparameters that you optimize to get the best results, right?
Yeah.
So how did you like optimize the hyperparameters?
Or we actually use a package under Python using research CV. So what the thing does is that it basically runs all the possible combinations of parameters, and it chooses the one that gives us the best results.
Okay. Oh, but it's not written in the code.
Yeah, it's not written in the code. We did write it here because it actually takes a very long time to run. So what it does is basically it takes in, depending on what you are trying to get, or what kind of parameters you're trying to tune. So in this case, let's say we are tuning 3 parameters, right?
Yeah.
So you put in an array of the values that you want to consider. Then you'll consider every single permutation of the 3 values, and you'll run every single thing on the model, and you choose it's basically doing the manual work for you to choose the best parameters. I mean the parameters that gives you the best.
Okay.
Yeah. Yes.
Yeah, explain a bit like the LSTM or the RNN, right? The back propagation, is it the same as a normal neural net? Okay, how does like the back propagation work for like LSTM? Yeah, like how they update the weights in LSTM? It's like my time step, right?
Yeah, correct.
I think it's the same abstract calculation because for each LSTM node, then you have like a gradient attached to it.
Yeah.
So in the forward prop, each of the gradients get sort of assigned. Then you go for back prop is to update these gradients, update the weights. Yeah, so my understanding is the same as the back propagation style.
So it's same as like normal neural net.
Yeah. So if you use like PyPlot, for example, you can actually like look at the gradients at each step. Yeah, then you can call dot grad as like auto grad in PyPlot. So you automatically update the gradients and you can actually view what the gradients are. It's actually on the question on the LSTM note, right? Why is it all the 10-page and sigmoid, all these actually I think they can be tuned also in PyTorch. So when you like download the LSTM, rather you import LSTM from the PyTorch library, if you want you can change the sigmoid to anything you want, like some other addition function or you break up the addition operator or multiplication operator. I think you can tune it if you want, but usually I think this is the standard that most people use. So as a package, I think this works well enough for most people, or most use cases. So people just use this as it is. So okay, fine. Any other questions? Feel free to.
Yeah. So this interesting small. So like, how does it generate new data points? How does it just duplicate them?
No, it doesn't exactly duplicate. It's more of like, if I'm not wrong, it looks at current data points already, and then it tries to. Because the current data points are basically there's a range to it. So basically, what it does is that I believe that it synthesizes new data points based on the current ones we have. So it kind of like it tries to make this sort of copies of it. It's not really duplicating. It's more of like making fake data that takes up all the space in between the range. That's like, you can try to fit in or Any more questions? We'll try our best to answer your questions. Yeah, if not, I think we've come to the end of our workshop. A bit early. You can hang around and have some meaningful conversations with each other. Thank you. Thank you for coming.
Yeah, you all want to take the tour also, then probably.
If you all want to book, you can send your.
Sorry, the down be cool.
That'll be cool. Okay. Perhaps you want to join the Zoom call or something, or maybe we will. How should we send it to them?
Send the IPYN file.
No, but yeah.
Download the file, then you send it to them.
Okay, is it okay if I get you to join the Zoom call? Then I'll just send it in the Zoom chat. Yeah. You just unplug. I think don't need to.